All right, let's go ahead and start Unit 6 here from Algebra 1, Illustrative Mathematics by Imagine Learning. We're on page 6 to 9 of your student workbooks. We're starting by looking at a different kind of change from what we've been looking at all year, and we're going to explore this a couple different ways. We're going to be looking first at a warm-up with 3 different tables to compare to the other types of change we had seen all year, and then we're going to be looking at this. I think it's best modeled with an area model to start to explore this change as well. So start with your groups. What do you notice and what do you wonder? Pause this video and see what you think. All right. As always, when we do our table work, we're going to want to do some marking up on the table. Noticing, for example, that the change on the left is just going up by 1. And we notice that across all the tables, the same thing is happening. So they have all the same inputs and they're all going up by 1. But we do notice that what's happening on the right-hand side is different for all of them. So for example, here we're noticing that this is just going up by 5 on each side. Do you remember all the vocabulary that we attached with repeatedly adding 5? You got it. It's called a constant rate. We also called that a common difference. When we're describing a pattern, we called that arithmetic. And when we're describing a function, we called that linear. So we want to throw all that vocabulary down for each of the patterns as we're noticing it. On this next one, we notice it's not adding repeatedly by the same number. Okay, but it is multiplying repeatedly by the same number. What did we call that? You got it. That was the common factor. We also called it the growth factor because this one is going up. We called it a common ratio, etc. So when we were describing a pattern or a table, we called that a geometric pattern or an exponential function. How are you doing with this vocabulary? Here we go to the new and final table. On this one, we notice that it's starting by adding 3, but it's definitely not repeatedly adding. Then we try multiplying by the same common ratio, but we notice that 11 divided by 8 is not the same as 10 divided by 11, so there's also no common ratio. Not adding by the same number, not dividing or multiplying by the same number, so it's not arithmetic or geometric. It's not linear or exponential. We would say that this is neither. And so this is our introduction to this new kind of pattern where it is possible for the pattern to go up and then to go down. So if your group noticed that it was increasing and then decreasing, you are right. That's possible in this new pattern. Well, did your groups happen to notice anything about the difference? If it's not a common first difference, did you notice that something is in common between these numbers? And so if you happen to notice that, that is called a constant or a common second difference. It's a difference of the first difference. And this, my friends, is what we call a quadratic. So what makes a quadratic is that constant or common second difference. That's how we recognize it from our table work. So we're going to do more work with that and start to recognize those regularly. So if you wrote any of that down with your groups in the warm-up, awesome. Next, we're going to be measuring a garden. Noah has 50 meters of fencing to completely enclose a rectangular garden in the backyard. Draw some possible diagrams of Noah's garden. So over here, we're going to draw one size rectangle, another size rectangle, another size rectangle. And we're going to start to think about what could the dimensions be if we have 50 meters of fencing. Well, how does a fence go? A fence is going to go around the edge, right, of that garden. So the 50 is actually our perimeter. So if you and your group have to come up with different ideas for how to spread out that 50, we also know something else about rectangles. These two sides, the opposite sides, have to be the same, right? Opposite sides of a rectangle are congruent. So if 50 has to spread around to all, for example, if I said that this was 5, then this would have to be 5. That uses up 10, and then I know that I have to split the difference. So 50 minus 10 is 40. 40 has to spread out to both the other sides. So some people like to think of this as just, well, let's just split the 50 from the get-go. 25. If I have 25 for half for each of the length and width, what other dimensions could we come up with? Well, some people thought of the smallest dimension. So a 1 by what? You got it, 24, because we've got 25, half of the 50 to split between the length and width. What else? You got it. If it's 2, then this would be 2 by 23 to make the 25. So 2 plus 2 is 4. 23 plus 23 is 46. 46 plus 4. All of these give us our perimeter of 50. Okay, well, did you notice a quick way to do this pattern? Every time this went up by 1, what did I have to do to the other length? I had to subtract 1. So we could probably think of all the possible combinations now that would work, but in particular, we want to find the length and width that would produce the largest possible area. Okay, so now this is giving us another parameter. So I'm going to go down here where there's a little bit of space because we're going to end up graphing it. And so we're saying if the smallest width was 1, we decided that was a 1 by 24, 2 by 23, we notice as one goes up, the other has to go down. Oops. So as the width is going up, the length would have to go down. But we want to know what creates the largest possible area. And the area would be the length times the width. So multiply these across for me. And with your neighbors, go, okay, which one created the biggest area? 1 by 24. I'm grabbing my little calculator now. 2 by 23. 3 by 22. Keep going multiplying that. 6 times 19. 7 times 18. 8 times 17. So are we noticing that as we keep going, this is getting bigger and bigger? 9 times 16. 10 by 15. 11 times 14. Now, when we hit 13 again, we start to notice some repeats. We notice then we get 13 and 12 again, and we get the 156. And then, so if I continue this pattern and this now goes down, we're just going to start to get all the same values again repeatedly. You see what's going to start to happen? This symmetry is another sign of this quadratic pattern. But now they want us to take the two columns of length and area, and go make a graph for this. So we used the width to get this table, but now we're going to ignore the width column, and we're just going to do length and area as our inputs and outputs. So length of 24 had an area of 24. So I'm going out 24, up 24. 2346, 2266, 2184, 2100. Oh, finally, something on a corner. 15150, another thing on a corner. Now, the highest it seems to go to here is 156, 12, 13, 156, and then 12, 156. And then that's when we start to notice the numbers coming down again. Okay, so essentially what we're starting to notice here is that this is going to be going in an upside down U-shaped fashion. If we took these numbers and actually put them into our graphing technology, it would be much better than my little sketch here. So because nothing's landing on corners, right? So what do you notice about the plotted points? We noticed that as we moved up in, well, let's say down in length, the area increased, but then it started to decrease again. So we're noticing that same pattern from the table above. It's increasing and decreasing in this new pattern. In our linear and exponential, it would only be increasing or only be decreasing. It couldn't do both in the same. Now the question you might be thinking is, did I really hit the top? Was this 156 point the actual top? Did anybody do decimal values to see if there is anything in between? The points 366 and 2266 each represent the length and area of the garden. Plot these 2 points on the coordinate plane if you haven't already done so. What do these points mean in this situation? So it means 3 feet long, or is it meters? Sorry. I think it is meters. Long is 66 meters squared in area and 22 meters long in length is also 62 meters squared in area. So let's go put those two, if we haven't already, 366. So picture this should have gone more like out here. And then 2266. And those are the same height. Could the point 125 represent the length and area of the garden? Explain how you know. No, we noticed that if we took 50 and divided it by 2, that the 25 had to be split up for length and width. So it couldn't be that 125 was our length and width, because that would total 26. So 125 does not work. And we're at the summary for our lesson. How'd you do?